Hi. All right. This is Objective 5.1, where I can use the Pythagorean Theorem, including in context. Got a penguin here that is super excited for this lesson because, yay, we're excited. Because this is one of, I think, the most useful theorems in geometry. So I'm excited to tell you about it. And so is our penguin power. Yeah. All right, here we go. Let's start with vocab. So first thing you know is a right triangle. A right triangle is a triangle with that right angle in it. That's 90 degrees. Okay? When we have a right triangle, we have a special name for the side that is largest, which will always be across from that right angle. We call that the hypotenuse. Then the other two sides, we call the legs. So sides that form that right angle, we call the legs. Okay, and we've got special names because right triangles show up all over the place. And so yeah, it's because they're super common. We've just got special names for them. Okay. Today's lesson is also going to involve a square root. So square root is this symbol. Okay. And that's if, like, let's say we have a number squared. Let's say like x, some value squared is 36. If I want to know what was squared got me to 36, I can take the square root to figure out what that value is. The square root is the inverse operation of squaring a number. And so that would mean x equals 6, because 6 times 6 is 36. A perfect square actually is when, we're going to go to square first. So a square can kind of mean two things. It's a shape with 4 equal sides. And then you get like 4 congruent angles, right? When we square a number, that means we take a number and multiply it times itself. So 4 squared is 4 times 4, which is 16. Okay, so this is when we square a number. We call that because when I take a number multiplied by itself, I'm actually like finding the area of a square. A perfect square is the result of an integer times itself. So 16 is a perfect square because that number came from 4 times 4. Or other numbers, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is again 16. These are all examples of perfect squares. More on that later. Okay? And approximate means not exact. Okay? So, here we kind of figured out what the Pythagorean Theorem is. We are going to jump over that and jump straight into our key points box. So I'm going to tell you the Pythagorean Theorem, which is just like a super useful theorem in geometry. It is when in a right triangle, the sum of the squares of the two legs is equal to the square of the hypotenuse. Okay, so basically, that's like a lot of language. So basically, if we've got a right triangle here, so if we've got our two legs A and B, when we square these two legs, make squares out of these two legs, so this leg is 4, this leg is 3, right? So 4 times 4 makes a square of 16, 3 times 3 is a square of 1, 2, 3, 4, 5, 6, 7, 8, 9. These two added up is equal to this hypotenuse. C squared, so this is 1, 2, 3, 4, 5, is 5. That's 25. Boxes, 9 plus 16 is 25. That's basically what the theorem is saying. We call it A squared plus B squared equals C squared. And so, for example, if we're looking at this right triangle here, and we're trying to find the length of the missing side, this is why this theorem is so useful, is that I know the two legs squared added up is going to equal the square of the hypotenuse. So, right here, the side I'm missing is the hypotenuse. We use the letter C to represent the hypotenuse. And the other two legs are going to be A and B. And then what that means is whatever A squared is plus B squared is going to equal to C squared. So a squared, so a is 5. So 5 squared plus 12 squared is going to equal my hypotenuse, c squared. So that means 25 plus 144 equals c squared. 169 equals c squared. Now, when I get to this point, you're going to have to take the square root because you want, this is c squared. So we don't want what c squared is, we want just c is. So taking the square root is the inverse operation of squaring something. Oops, sorry, so that's going to give you just c. It's going to undo the squaring. And so I'm going to have to do this to the other side. In your calculator, how you achieve that, in this type of calculator, is second square root. Punch in your number. So second, your square button. And that gets you to 13. Which makes sense because 13 squared is 169. So this is, again, this is how you square something in a calculator, this button here. So square root that, you do second, and you look for that square root symbol. See how it's in purple? That's why I hit second, because now this button is going to do the purple thing, not the white thing. So when I hit it, the square root symbol shows up, and then I get 13. Okay, so this hypotenuse is 13 units long. Okay? The hypotenuse, or the Pythagorean theorem will also tell you if you're not dealing with the right triangle, what type of triangle you are dealing with. So if c squared ends up being greater than a squared plus b squared, then the triangle is obtuse. Meaning it's a triangle that's got an obtuse angle in it, like that. If c squared is less than a squared plus b squared, then the triangle is acute, meaning we can expect all the angle measures to be less than 90 degrees. Okay? So we're going to use that idea for examples 2 and 3, which is asking, is this a right triangle? Explain how you know. Well, I'm going to use the Pythagorean theorem. So I'm going to label, so Pythagorean theorem says a squared plus b squared equals c squared, where again, c represents my longest length. So my longest length here is 6.4. I'll make these two a and b. It doesn't matter which one you make a and b because a squared plus b squared is the same as b squared plus a squared. So let's plug in 5.6 squared plus 2.5 squared. Now we're trying to see, does that equal 6.4 squared? If it's a right triangle, it should. So I'm going to do that math. So 5.6 squared is 31.36 plus 2.5 squared is 6.25. Now, does that equal whatever 6.4 squared is? Let's see what happens. That's 40.96. So let's add 31.36 plus 6.25. You get 37.61. Okay, so noticing that is not equal to 40.96. 40.96 is bigger. So my c squared value, when I took what c was, and I squared it, right? I end up getting something larger than a squared plus b squared, so that means my triangle is obtuse. It's not right because they're not equal. It's an obtuse triangle. So the answer here would be like, no. Is this the right triangle? No, because a squared plus b squared doesn't equal c squared. Okay? Now this example wants me to classify the triangle as acute, right, or obtuse. So I'm going to do the same idea. I'm going to do a squared plus b squared equals c squared and see how a squared plus b squared compares to whatever c squared is. Again, c has to be my longest length. So that's 35 squared. 16 squared plus 30 squared. Let's see what happens. So they end up being equal. 16 squared is 256 plus 30 squared is 900. Let's compare that to 35 squared is 125. What's 256 plus 900? It's 1156 compared to 1225. Oh, c squared ends up being larger, so this is an obtuse triangle. Okay? All right, so now we're going to jump to page 3. Okay. Page 3 is about, we just did a lot of calculations there, right? A way you can save yourself some time when dealing with the Pythagorean theorem is using Pythagorean triples. Triples are a set of 3 integers that satisfy the Pythagorean theorem. write that down. I'll be right back. Okay, so multiples of the Pythagorean theorem will also work, so I'll explain what that means in a second. So basically, these are triples. So these are numbers that we can always say, like these three sets of numbers will, my a squared plus my b squared will always equal my c squared. So 3 squared plus 4 squared will equal 5 squared, which is 25. Okay? Or same thing here, 5 squared plus 12 squared will equal 13 squared. And so, what's dope about that, hey, can someone get the phone for me? Just someone answer. Just Miss Feifel's room. Then see what they need. Thanks. Okay, so I just can't pause this video. So, what's dope about this is, look at this. I have 5, 12, and I want C. Who is it? Oh my God. Okay. I'll be right back, video. Enjoy this penguin real quick. So hopefully you've been thinking about what makes triples happen. Okay, and so so we noticed this one. We don't even have to do the Pythagorean theorem. If we notice that 5, 12, 13 is a triple, 5, 12, bam, we can know automatically that's going to be 13. Okay? And then what's cool about this is like multiples of this are also triples. So if I were to take like 3, 4, 5 and make it 6, 8, 10, that's a triple too. Or that would be a triple too. Because it's the doubled version of 3, 4, 5. Okay, so that's just like a little side time saving tip. Okay? Next thing we're going to talk about is if examples, how to make sure that if we're using the Pythagorean theorem, we get exact answers. Okay? So, you've noticed that when we have been using the Pythagorean theorem, we're dealing with the square root, right? So I'm going to tell you a little bit more about this symbol. This symbol is also called a radical. So, this is the radical symbol. Okay? And so that means this whole thing, this whole quantity, we can actually call it a radical if we want instead of a square root. Okay? The number under the radical symbol we call the radicand. This we call the index. It just means like what root are we finding? The square root, the cubed root. Okay? And so simplifying radicals works like this. If I take, let's say I'm taking the square root of 12, and the last step of the Pythagorean theorem, and I want to take the square root of 12. The square root of 12 is this, right? That's not exact, right? If I were to change it to a decimal, because it's a big long number. So it's more exact to leave it as a square root. However, we can simplify the square root and make it look a little bit smaller. How we do that is we're going to rewrite the radical as its factors. Okay, so if I think of rewriting the square root of 12 as the square root of maybe 4 times 3, because 4 times 3 is 12, then if I remember that the square root of 4 is 2, this is 2 square roots of 3. You can rewrite this as 2 square roots of 3. And notice 2, like remember that decimal value? 2 square roots of 3 is that same value. So that's just the simplified version of the square root of 12. So what we're learning here is a radical is said to be in simplest form when the radicand has no factors that are perfect squares. Okay, other than 1, right? So when I say perfect squares, I mean, again, those integers squared. So 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. I recommend getting really familiar with these numbers. Okay? And then to simplify the radical, what you do is rewrite the radical as its factors. One of the factors must be a perfect square. Okay? And so, yeah, the thing to know here is like, we can take a radical, a product under a radical, and split it into its factors. Okay? So I'll do a few more. I'm not going to do all of these. It's a lot. I'm just going to do a few more, right? So for example, the square root of 50, I'm going to rewrite it as its factors, but I'm going to make sure one of my factors is a perfect square. So when I think about numbers that go into 50, 1, we're not going to do 1. 4 doesn't go into 50. 9 doesn't go into 15. 16 doesn't, but 25 does. So I can rewrite this as the square root of 25 times the square root of 2 and rewrite it as 5 square roots of 2. Make sense? Okay? And we want to make sure you pick the largest perfect square that goes in. So we're going to jump straight to, if we were to rewrite the square root of, I'm actually going to skip this one. We're going to think about rewriting the square root of 32, right? So if I rewrite the square root of 32 as the square root of 4 times the square root of 8, 4 is a perfect square, so that becomes 2 square roots of 8, right? However, I can also rewrite the square root of 32 as the square root of 16 times the square root of 2, which would become square root of 16 is 4, square roots of 2, right? This is the most simplified answer because the square root of 8 can still be broken down because it's got the square root of 4 inside of it. Right? So then this would become, the square root of 4 would become a 2. So I'm just dropping this down here. And we'd still get 4 square roots of 2. You just have to simplify twice if you do it this way. So find the larger perfect square that's a factor. Okay? Last thing I want to show you on this is, hey guys, if I'm looking at you, it's because I need you more focused. Okay? I hope we're making good progress. I'll be done with this in about 5 minutes, and then I'm going to come check your progress. Last one I want to show you is like, well, what happens if I have like a number out front? So 5 times the square root of 18. Simplify the radical like I did in these examples, where I'm thinking, okay, what perfect square goes into 18? I notice, oh, 9 does. So square root of 9 is 3. So I get to rewrite that as a 3. Then all I'm doing, guys, is I bring it down by 5. This is saying 5 times the square root of 18, right? So now I'm saying 5 times 3, you get 15 square roots of 2. That's what that would simplify to. So just make sure you're like bringing down and multiplying through if there's a coefficient in front of the square root of 18. Okay? Or this one. This one's tricky because look, this is immediately a perfect square. Square root of 36 is 6. I get to change this to 6 immediately. Bring down my 7. That simplifies to 42. This is a fancy way of saying 7 times 6. I just had to simplify the square root of 36 into 6. Okay, I'm going to leave you to do these examples on your own. last thing I'm going to show you is on page 8. Now, why I said I loved this theorem earlier is because right triangles show up all of the time, and in actual real life context. So I want to show you a couple of real life contexts that they show up in. Okay? Okay, so Pythagorean is using contexts that require a lot of indirect measurements. That means you need to, you can use a right triangle to represent the situation. Okay, and then because it's useful, because then we can start like solving for distances and stuff, okay? So for example, what was the original height of the tree in feet? Okay, so if we have a tree that split, and you were wondering how tall this tree was, okay? Look how it split. When it split here, it formed a right triangle. Well, look, if I know that this is 10 and that's 24, then like, hey, this is just the hypotenuse of a right triangle. So that situation, the tree, I'm going to color in the tree. There's the tree, right? It's split. It forms a right triangle. So then I can do a squared plus b squared equals c squared. I'm going to actually notice this is a triple. It's the doubled triple of 5 and 12. So c would be 13. Doubled would be 26. You could also do 5 squared. You could also do 10 squared plus 24 squared equals c squared and solve that to get to the 26 too. Okay, it's just a doubled version of the Pythagorean triple 5, 12, 13. Okay, so cool, that's how long the tree was. Okay, or this situation, Pythagorean shows a lot if you're gonna like ever use like ladders. So let's say Bob has a 20-foot long ladder. The instructions for the ladder, I'm telling him he should put the bottom of the ladder 15 feet away from the base of the building. What was the exact height of the tallest building that Bob can scale using his ladder? Okay, so he's leaning a ladder against the base of a building. So I'm going to draw, when I think of a building, I think of a vertical height, right? Then a ladder, he's leaning the ladder against the building. So that's a diagonal, right? The instructions say that the bottom of the ladder should be 15 away from the base of the building. Here's the base of my building. I mean, if you need to draw yourself a little building, you need to draw yourself a little ladder. But again, this is a situation where a right triangle is showing up, right? Base of the building, bottom of the ladder, is that horizontal length. If I were to measure that, that forms a right angle, and thus we get a right triangle. Right? So, the ladder is 25, right? It's 15 feet away from the base of the building. Basically it's asking how high would this be? What's the tallest that we can get to? Now let me look. Is this a triple? Let me see if this is a triple. I'm looking at 25 and 15. Okay, this isn't a triple. Okay, so I'm going to do the math. So I'm going to do a squared plus b squared equals c squared. Okay, where this is c, it's across the right angle. I'll make a 15. I'll leave b as the thing I'm trying to find. Get 25 squared. 15 squared is 225 plus b squared equals 25 squared is 625. And we want the exact height. Minus 225. Oh, is this a triple? My bad. B squared equals 400. Square root, square root. Oops, delete. And B equals 20. So 20 feet is as high as that ladder will go. Okay? My bad, that is a triple. That's actually, it's a multiple of the 3, 4, 5 triple I'm seeing now. All right. That's it. Hope you enjoyed.